This is the video lecture for shear and moment in beams under load. And what we've done before is found shear and moment at a point. And we did that by drawing a little section, a little squiggly thing there, and then we drew a free body diagram of that piece, which is the shear. We drew positive shear and positive moment, and we solved for shear and moment by summing forces in the y direction and summing the moments about a point. All right, and we did all that before. We drew, remember, had to keep track of positive shear and positive moment. What we're going to do today is do the general case, or understand the general case, when you want to find the equations that define shear and moment for the entire beam. Here, there are equations that are going to be valid between discontinuities, and a discontinuity will happen every time there's an applied force or a reaction. So where this reaction is, as a beginning of a discontinuity, but here we have an applied force and the beginning of a distributed load. Right here, that's going to be a discontinuity, and then another one. And then we'll have another applied load, and another reaction. So every place where there is a change in the application of a force, there will be a discontinuity, and we'll talk about those as we go along. All right, so the way we're going to solve these things is, first of all, treat it as a rigid beam, find the reactions that you can find, and then recognize the discontinuities. And then what we'll have to understand is there's a separate equation that's required for the shear, a separate set of equations that are required for shear and moment between each discontinuity. All right, and when we do that, we'll be able to graph those equations as well. So this is a section from the book, very good beginning here of shear moment equations and diagrams, so I encourage you to read this. But here's a couple of pictures here that I wanted to just show you. But here we have a beginning of a distributed load, and we have a reaction, of course, but there is going to be a change in the shear between this point and this point. And you can see that that is the shear going linearly down. Where there is an applied force, there's going to be another rapid change in the shear, and then where there is a reaction, there'll be another discontinuity or another sudden change in the shear. So we'll again understand that as we go along. But in between, right in here, where there is no where there is no change in forces or anything like that, that says that the shear doesn't change in between these 2 points. So, and you can see that that is the case here, where we're between applied loads, the shear is constant. The same thing between here and here. And then we see that right here is that the shear is constant between those points. And we'll talk a little bit more about moment as we go. All right, so first of all, I want you to do these fundamental problems. I put these on Mastering Engineering, so I'm not going to grade them, but you definitely need to do them and understand them. And let's just get started with this first one. It's an example problem, actually. And let's find out what see if we can discover the shear and moment general equations for this beam. All right, first of all, it's got a 5 kilonewton force, and there is going to be an AY and a CY right there. CY and AY. And we can find those by some of the forces and some of the moments and find out what those reactions are. All right, let's draw a little section right here, and let's do a little diagram like that. And here we have this is 2.5. We're going to do positive shear, positive moment. And sum the forces in the x and y, or sum the forces in the y, and try to find out shear as a function of x. All right, so sum of the forces in the y is equal to 0. So I got plus 2.5 minus shear is equal to 0. So shear is actually a constant here of 2.5. And during this lecture, I'm going to leave off the units just to save clutter here and make sure I don't make any mistakes using units. But I encourage you to use the units on your homework and, of course, on your exam. All right, how about moment? What is moment here? So sum of the moments about A is equal to 0. So what have I got? I got minus shear times the distance x plus moment is equal to 0, and I can find the moment is actually equal to 2.5x. All All right, so those are the equations that are valid between A and B. All right, let's find out what happens between B and C. So let's draw another little section there. And I'll draw this little squiggle. And I got a 2.5 here again. Here I've got my 5 kilonewton applied force. Then I got a shear and a moment there acting at a distance x. So let's sum the forces in the y direction here. Let me draw a little separation there. So forces in the y is equal to 0. So here I've got plus 2.5 minus 5 minus shear is equal to 0. And so shear is equal to negative. Let me get rid of that. Do that over here. Shear is equal to negative 2.5. All right, how about moment? Sum of the moment about A is equal to 0. So here I got negative 5 times the distance of 2. This distance here is 2. Minus shear times x plus moment is equal to 0. And then I got moment is equal to 10 minus 2.5x. All right. So now, and these are the equations that are valid between B and C. All right. So that doesn't look too hard yet. We're going to get some that are a little more difficult than that, but now we can graph those equations. So let's just do that. And I'm going to graph those right underneath my picture, right down here, and do something that looks like this. So here I'm going to have a shear graph. Come on. And a moment graph. All right, let's see what the moment looks like. Or let's look at the graphs of both of these things. So shear says it is equal to constant 2.5 between these 2 points. So that is going to be a constant. Then it's equal to a constant negative 2.5, something like that. Now what happens at this point? Well, this is the discontinuity that I was just talking about. And that's kind of the way the shear graph looks. And inside here, this business right in here, that's the discontinuity. Okay, how about the moment graph? Let's go back to that. Moment looks like it increases linearly from 0 to here, and then it decreases linearly from here to here and ends at 0. How do I know that? Well, if I were to put the value of the moment, or I can compute the value of the moment at any point by putting in the distance x. So let's say at x is equal to 4. Let's see what we can find the moment. Well, moment is equal to 0 at x equals 4. If we go back to the top of the picture there, x equals 4, moment's equal to 0. How about at x equals 2? And moment is equal to, well, it's 10 minus 2.5 times 2, so moment is equal to 5. And then I can find the peak moment here. It looks like 5 right there. These, of course, are 2.5 and negative 2.5. All right, let's keep on going. Let's see if we can do it on just a little bit tougher. Here we have 2 forces that are applied to this beam. And let's draw the reactions on here first. And there's going to be an AY and a, well, let's see. I don't have any letters on here, so let's put some letters. We got A, B, C, and D. So I can do my, well, actually, you know what you can do here is by symmetry, because these are equal distance on both sides, equal distance there in the middle. So by symmetry, you can take these shortcuts if you're comfortable, but it says that AY equals DY equals 800. Because each of the applied forces are equal to 800. All right, I'm going to shortcut the process just a little bit, focus on the shear and moment graphs, but what you do is recognize again that there is a discontinuity that happens between these applied forces, and you have to have a separate set of equations that applies here. So I need a set of equations that applies between A and B, a set of equations that applies between B and C, a set of equations that applies between C and D. And so I do all that by drawing little sections, drawing a squiggle line first, and then drawing a section, and writing the equations. Then I do another one, write the section, another one, and then draw a free body diagram of the section, write all the equations out. And now let's do the graphs. All right. So let's do that by drawing the graphs right underneath these applied forces. Kind of like that. Actually, those don't quite line up, but that's all right. So let's do a shear graph that looks like this, and a moment graph that looks like this. All right, what do the shear and moment look like? Looks like shear is positive 800, and this is curious here. If I look at the shear on this middle section here, it says it goes to 0 right there in the middle. And looking at the graph, looking at the picture, I don't think it's very obvious that it would be. It's not obvious to me anyway that the shear is equal to 0, but when you calculate it, it is. So I'm going to draw the shear goes to 0 right there. Then it goes to negative 800, and that's what the shear graph looks like. Whoa. Okay, so sorry, we had a little glitch here in the electronics. All right, what's the moment graph look like? Again, it looks like it's increasing linearly here. It looks like it is where shear is equal to 0, then moment doesn't change. And so it looks like moment is a constant here, and then it has a linearly decreasing picture. So it looks like this, flat, and then down like that, where these are going to be lined up like that. All right, what are the values here? Well, I've got this is equal to 800, and it goes to 0, and that's minus 800. What's the peak value of my moment? Well, I can do that by just say, well, I guess I've already solved for that right there. It's pretty easy because that one was solved for us already with 4,000. All right, how about this one? A little bit tougher yet. This is a cantilever beam, and we haven't done a lot of cantilever beams yet, but I'm going to keep throwing them in here. I hope that you can grasp these concepts. But this has a reaction, an AY, and cantilever beams always have a moment about A, and sometimes there's an AX. There would only be an AX if there's some applied force pushing or pulling on the outside here, but in this case there isn't, so there isn't going to be a value for AX. But doing their proper equations, we can see that AY is equal to 100, and MA, that moment about A right there, is equal to 1800 right here. Now we're going to draw some little squiggly lines. I'm going to do a squiggle here and then draw a free body diagram of that. So these are going to be the equations that are valid between A and B, and then do another section and draw another section, another free body diagram, and these are going to be the equations that are valid between B and C. Okay, with that, then let's draw the diagrams. Okay, again, let's put our diagram right underneath the picture, such that we got a shear diagram and a moment diagram. And let's see what those look like. Well, sometimes you can't really just start drawing the diagram until you have some values. So let's look at what the value of the shear is going to be. The shear, if I look carefully at the work that I've done, it looks like shear is equal to 100 here. So that's going to be 100 down here, from here to here. Then I look down here, and shear is going to be equal to 100 again. So it looks like the shear is constant across the beam. It's interesting. It does have an applied torque right there, a couple, which we need to kind of keep track of, because sometimes we have beams that have couples on them. Let's look at the moment diagram now. The moment, if I look at this equation right here, the moment is going to be, no, I beg your pardon, not that equation, but this equation right here. Here's the moment diagram, or moment equation that's valid between A and B. And if I look at that, it has moment at x equals 0, then moment is equal to negative 1800. So it begins at negative 1800. Then it looks like it's getting a little. The shear begins at negative 1800, but increases linearly. And that's what we see right here with this, that term right there. And if we look at the, what we can do is we can put in values of x and find moment at any particular location along the beam. So let's find out what the moment is at point B here, and I'm going to put x is equal to 5. So if I say that moment is equal to negative 1800 plus 100 times 5, I can see that moment is equal to negative 1300 at x equals 5. So I'll just put that there. So I'm going to draw it goes linearly right up there to negative 1300. So negative 1800 and negative 1300. All right, let's look at the moment for the second section of the shear moment. Well, I guess I've already done the shear. So the moment for the second section. And here's the equation that defines that. And it says that a moment is equal to negative 1000 plus 100x. So let's see what let's put the moment here at x is equal to 5 as well. So I'm going to say the moment here is going to be equal to negative 1000 plus 100 times 5. And I see that that is equal to negative 500, which is kind of interesting. So anyway, that's another value for the moment at that point. And then if you put x is equal to 10, equal to negative 1000 plus 100 times 10, and that you can see that it ends at 0. So it goes this way and ends at 0. All right, what's going on here? This is another discontinuity, and that's a moment discontinuity here. The shear is constant, as you can see. It's constant along that whole line, but moment has a discontinuity right here where there's an applied, right there where there's that applied moment. So that little couple right there causes a sharp increase in the moment, and we'll talk a little bit more about that as we go. All right, last problem here is where we have distributed forces, and these got a little bit more complicated, but I've already found the values of AY and BY. Let's put them on the picture here. So we have AY and BY. I've already done my little squigglies, and I drew a section here. And so this is my section for here, and I drew it right here. Now, let's look carefully at what we do here with distributed forces. We draw the distributed force in at the same, I guess, weight per foot, the 50 pounds per foot, as it is in the big picture, but we only draw a portion of it as a function of x. And you can see that if x is here, then the resultant is going to be 50 times x, because that's going to be 50 times that x, and that it acts at a distance x over 2, because it's going to be halfway between the total length. So that's kind of a key thing to keep track of when we have distributed forces, is that the resultant acts at x over 2. Now we do some of the forces in the y and some of the moments, and we can find out what the shear and moment equations are. So some of the forces in the y, and I got that. Some of the moments about that equals that, and I got shear and moment equations as functions of x. All right, so I want you to walk through the math here and make sure you understand that. Look carefully at that. We'll do some more of that in class tomorrow. But now let's look at the shear and moment equations for this section out here. Again, draw free body diagram, that section right there. And let's draw write the equations. Some of the forces in the y, and it turns out that shear is equal to 0 out there. And then it turns out that moment looks like it is constant. So let's look carefully again at what's going on out here. There aren't any applied forces. So it sounds like the shear ends at 0, and it doesn't have any change out there. And it looks like the constant moment is counteracted then by that couple that's at the end. But again, we'll talk a little bit more about that on Wednesday. But here are the valid shear and moment equations for those two sections. All right, so let's draw the diagram then. Let me draw the lines coming down, and I'll draw the shear graph and the moment graph. Let's look what it looks like. All right, shear as a function of x, if you were to put x is equal to 0, we can see that shear starts at 490. So it starts up there at 490. And if we look at x equals 20, shear is equal to negative 510. So it looks like it decreases linearly like this down to negative 510. So it starts at 490, it increases linearly. Then it is 0 after that. So we can, that means it goes back up here and then is 0 after that. All right, how about the moment equation? Moment at x equals 0 is going to be 0. That's what this is all about. If we look at that, so it starts at 0, and then it looks like, because it's a function of x squared, it is a quadratic. Let's find out what the value is at x is equal to 20. Moment at, let's put it here. At x equals 20, moment is equal to negative 200. Negative 200. So let me just put that in there. It is a quadratic, so it goes up like this and then goes down like that. And then it says that it is constant at negative 200 and then goes back up to 0 at that at the end here. All right, so that's a picture of the graph. Now, what is the peak moment here? The peak moment, as we will discover again, or we will soon discover, it comes where shear is equal to 0. So if I can find out where the shear graph equals 0, I can find out what the peak moment is. Well, how can I find out what that is? Well, I can solve this equation here, shear as a function of x, where shear is equal to 0. I can say, where shear is equal to 0, x is equal to 9.8. So this distance right here is 9.8, and then I can do this down here, and I can solve this equation here at 9.8. I can get shear moment is equal to 2401. So that is the peak value there, 2401. It occurs where shear is equal to 0. All right, we'll talk more about this later, and we'll conclude this for now.